This video is going to be about bases. Bases are relevant to how we write numbers. But what does it mean to be in base 10? Or what does it mean to be in base n? In this video, we'll talk about it and give an example problem at the end. Before we talk about bases, we need to talk about what a number is. Numbers are mathematical objects that are used to count or measure. One way we can think about this is that numbers represent quantities. For example, drawing on the left 6 dots, the number is 6, representing that quantity. So 6 is the number, and the amount on the left is the quantity. Since numbers represent quantities, we need to think about how we write a number and what it means. First, let's talk about how numbers are composed of digits. So these are two separate things. For example, we can have a number, 14,271. The digits in it are 1, 4, 2, 7, 1. These are separate from the number. Our number system is going to describe what the number means by declaring a base and a place value. So the base refers to how many digits we have that we can represent numbers with. In base 10, we would have the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9, which is 10 choices of digits. In base 4, we would only have 0, 1, 2, and 3, meaning 4 choices of digits. And in base 6, we have digits 0 through 5, which is 6 choices of digits. To base n, this means we have digits 0 through n minus 1, so that we have n digits. Base 10 is most commonly used today, but it hasn't always been that way. Ancient Mayans worked in base 20, while ancient Babylonians worked in base 60. This means that Babylonians had to have 60 different characters to be their digits. So why is base 10 so commonly used? Historians think it's because a lot of civilizations base it off of us having 10 fingers. Now that it is this way, it's really hard to change, so it's likely we'll keep using base 10. We do use the binary system, which is base 2, a lot in computers. We're also familiar with seconds, minutes, and hours, which are in base 60. We can see this because 60 seconds forms 1 minute and 60 minutes form 1 hour. Although we're used to working in base 10, we can actually still represent any quantity in different bases. This is because of the place value. The place value is the numerical value a digit has due to its position in the number. In other words, digits mean different things depending on where they are in the number. In base 10, we're familiar with the place values of ones, tens, hundreds, and so on. Notice that 1 is 10 to the 0, 10 is 10 to the 1, 100 is 10 squared, and this pattern repeats, meaning that the nth digit, or nth place value, has value 10 to the n. We assign these place values from right to left, with the smallest being on the right and the largest being towards the left. In the first place value, we have 1s, or 10 to the 0th, and that goes on until the nth place value, which has value 10 to the n. For example, in base 10, 3,472 means that we have 2 1s, 7 10s, 4 hundreds, and 3 thousands, which are 10 to the 0, 10 to the 1, 10 squared, and 10 cubed for each place value. In base n, it's a similar pattern, n to the 0, n to the 1, n squared, n cubed, and so on depending on the size of the number. For example, in base 6, 1, 3, 4, 2 means we have 2 6 to the 0s, 4 6 to the 1s, 3 6 squareds, and 1 6 cubed. So we have an amount of 2 1s, 4 6s, 3 36s, and 1 216. You might remember learning about place values in base 10 using these manipulatives called base 10 blocks, where there's units, longs, flats, and cubes representing 10 to the 0, 10 to the 1, 10 squared, and 10 cubed. We can actually do the same in different bases. In base 6, a long would have 6 units, a flat would have 6 squared units, and a cube would have 6 cubed units. Another place we can look for bases and how to represent them is in games we play. For example, in Monopoly, you can buy a house for $100. Then you can buy multiple houses, but by the time you reach the 5th house, you can't have 5. You swap it in for a hotel. So you know that a hotel represents 5 houses. Similarly, we know that poker chips represent different values. For example, the white one could represent 1, blue 10, and black 100. So we could think of those as base 10 pieces. We could also have white as 1, red as 5, and green as 25. So these are base 5 pieces. Based off the values we assigned, 5 white pieces would make up 1 red piece. And then 5 red pieces would be equal to 1 green piece for 25. Let's do an example problem on how to translate from base 10 to some base n. In particular, when we're going to do the problem turning 59 base 10 into base 5. There are multiple ways to think about this problem, but I'm going to show you 2 different methods. We want to turn 59 base 10 into base 5. So 59 is 5 tens and 9 ones. But really, 59 is a quantity. So for each one of these 10 chips, we can actually just replace it with a stack of 10 ones. Let's shuffle them all around to remember that 59 is really just a quantity. Now, we want to turn this quantity of chips into base 5. So in base 5, we write numbers with different place values than in base 10. Now our place values are going to be 5 to the 0, 5 to the 1, 5 squared, 5 cubed, and so on. In base 10, 5 to the 0 is 1, 5 to the 1 is 5, 5 squared is 25, and 5 cubed is 125. Notice that 125 is a lot bigger than 59, so we actually won't need to use this place value at all. We're going to be looking for how many 25s we can form, how many 5s, and how many 1s. We want to form as many groups of 25 as possible. We don't want enough 5s left over that you could form any more groups of 25. So we're going to start by pulling out as many groups of 25 as we can. We're going to count out 25 1 chips and replace it with a green 25 chip for every group of 25 we find. Now that we've removed 25 1 chips, we replace it with 1 25. We're going to repeat this as many times as possible. Notice that we're left with 9 1 chips. This means we can't form any more groups of 25. That means we've found a maximum of 2 groups of 25. So we're going to fill in a 2 in our 5 squared part. Mathematically, what we just computed was 59 divided by 25 is equal to 2 with a remainder of 9, where 2 is what we're going to put in our 5 squared spot. Next, we want to repeat to find the maximum number of 5s that we can pull out of our remaining number. So we're taking our remainder of 9 and dividing by 5 to see how many groups of 5 we can form. Let's do this with the poker chips. For every group of 5, we can replace it with a red 5 chip. After doing that only one time, we're left with 4 1 chips, so we can't form any more groups of 5. Mathematically, 9 divided by 5 is equal to 1, with a remainder of 4. 1 is how many groups of 5 we have, so we place a 1 in the 5 spot. Finally, we're going to see how many 1s we need. We see that we have 4 1 chips, which is going to be 4 1s. To keep the pattern of the equations, we could write that 4 divided by 1 is equal to 4 with a remainder of 0. So 4 is in our 1s spot. We have shown that 59 base 10 is equivalent to 214 in base 5. Let's consider the same problem, but using a different method to solve. "59 in base 10 would require 5 10 chips and 9 1 chips. To think about it in base 5, we want to first turn all of our chips into single unit chips. So instead of each of these 10 chips, we're going to replace it with a stack of 10. Now we have 59 single chips. Since we want it in base 5, we're going to be trying to form groups of 5. And then once we form groups of 5, we'll want to try to form groups of 25. We won't need to look for groups of 125 or 5 to the third because 125 is greater than 59. First, let's look for how many groups of 5 we can form. For every group of 5 I pick, I'll replace it with a 5 chip. We're left with 4 single chips, which doesn't form a group of 5. So we're going to keep these 4 chips here. Let's keep track of what we just did mathematically. We computed that 59 divided by 5 is equal to 11 with a remainder of 4 because we have 11 red chips. Okay, so we know that in our ones place, we're going to have 4. Next, we're going to try to form groups of 5 out of our remaining chips. So we're going to move our 11 to here and repeat the same process. We want to do 11 divided by 5 and see how many groups we can form. Forming groups of 5, we're going to replace every 5 red chips with a green 25 chip. So here's 5 red chips, and we'll replace it with 1 green chip for 25. So we see that 11 divided by 5 is equal to 2 with a remainder of 1. Now, 1 is going to be in our 5 spot because we only had enough for 1 5. Next, you can probably see already what's going to happen, but we'll repeat the process so that you can see how it works. We're going to take 2 and see if we can form any groups of 5. So 2 divided by 5 is equal to 0, remainder 2. That means we have 2 in our 25 spot, which makes sense because we don't have enough green chips to form another group of 5. As a result, we can see that 59 base 10 would translate into 214 base 5, where the 4 represents how many 1s we have, the 1 represents how many 5s we have, and the 2 represents how many 25s we have. This amount of chips is equivalent to having 59 base 10. Let's compare the two methods that we just did. In both problems, we were really dealing with the same problem, turning a quantity of 59 base 10 into base 5, meaning that we only have 5 digits available, 0, 1, 2, 3, and 4, and our place values were different, being 5 to the 0, 5 to the 1, and 5 squared. For both problems, we recognize that we didn't really have to work with 5 cubed, because 5 cubed in base 10 is 125, which is greater than 59 base 10. That quantity is bigger, and so we wouldn't need to represent the smaller quantity using 5 cubed. In the first method, we were trying to fill in the place values from left to right. we wanted to take out the biggest group of 25 that we could and do that as many times as we could so we would know how many should go in the 5 squared spot. We did that by dividing 59 by 25, which resulted in 2 groups of 25 and a remainder of 9. Using that remainder, we divided by 5, the next place value, to see how many 5s there would be. We found that there was 1 group of 5 and 4 left over. Taking those 4, we were going to turn them into 1s. 4 divided by 1 is 4, with a remainder of 0, so we knew that there would be 4 in the 1 spot. In the next method, we were recognizing that really each of these place value is a power of 5. Once we took out 5, we could make those into more groups of 5, or 25. So what we were doing is taking out groups of 5 from 59. Our remainder was how many units couldn't be turned into groups of 5, so that was going to go in our 1 spot. Then we take each of the groups of 5 we formed, and those were our red chips. We wanted to see, with the number of 5s we had, how many could become 25s. So we divided 11 by 5 and found that it was equal to 2 with a remainder of 1. This means we're able to form 2 25 chips and have a remainder of 1 red chip that can't form another group of 5. So 1 goes in our 5 spot. Finally, we repeat the pattern. 2 25 chips is not enough to make another power of 5. So 2 divided by 5 is 0 with a remainder of 2. And that means we have 2 25 chips. For both, we end up with the same answer as we should, but it's just 2 different ways of thinking about converting from base 10 to base 5. You can use this method for other bases. I just used 5 so that we could use the poker chips as an example. And you can do it for numbers that have far more digits than 2,